Welcome back, everybody, to day 5, final day of EA Global Summit, virtual conference connecting global EA practitioners. This is Juhi from Summit team, and this is my last session of the summit as host. I would like to take a few seconds to thank all speakers in sharing their knowledge and conducting workshops in various topics. As I said before, the time we had between when we started this idea of conducting this virtual conference and now is just 3.5 weeks. With presenters' contribution in quick span of time, made this event possible. So thanks all presenters, thanks all speakers. Finally, thanks all for showing fabulous participation in this conference. We have had around 1,400 individual registrants for this entire summit. And for each session, we had around 700 plus registrations. We are still having 2 more sessions for this day, and they are all exciting topics too. Please stay connected with us. For this session, we have Colin from Craft Prospects presenting here enhancing ROKS space mission design with Sparx Enterprise Architect. Just to bring your attention once again, we have the Teams channel ready for Colin in his name, and you can connect and interact with Colin after this session and throughout the summit with other practitioners too. Please refer to the chat window to find the link. Now over to you, Colin. You can now present your session, and I'll make you as presenter now.
Okay, hello. I'm Colin Aiken. I work for Craft Prospect based in Glasgow, Scotland, and today I'll be presenting our ROKS mission and how we've used Enterprise Architect to enhance our mission design. So I originally studied chemical engineering at Heriot-Watt University, but I decided I wanted to pursue a career in the space industry. So I decided to go back to university and do an advanced mechanical engineering with aerospace degree at the University of Strathclyde. After I completed my degree, I joined Craft Prospect through an internship program ran by the Satellite Applications Catapult. That's when I first started on the ROKS mission. And then after my internship, they ended up keeping me on to help provide systems level support to their ongoing ROKS mission. During my time at Craft, I also was sent to Rome to take part of the European Space Agency's 5-week bootcamp, where my team took first place for our work in forest fire prevention in Portugal using Earth observation data and AI. So Craft Prospect is a new space company founded in 2017, focused on new space technology, systems engineering consultancy, and collaborative research on enabling technology. Our main areas of research at the moment are security, quantum, and AI. The ROKS mission sees a combination of all three. During this presentation, I hope to provide some examples of how we've used Enterprise Architect during our mission. And also I'll give a wee background on ROKS, the methodologies we used, again, some examples, and then my own personal thoughts on how I've experienced it during my short time at Craft. So what is ROKS? ROKS will be an in-orbit demonstration of quantum key distribution mixed with responsive operations. Those two things I will explain later. Basically, it's going to be on a 6U CubeSat. These are just really, really small satellites, also known as nanosatellites. A 1U just means it's a 10 by 10 by 10 centimeter cube. So the 6U is a 30 by 20 by 10 centimeter like cuboid. The CAD model on the slide shows our current design. We are only responsible for the payload section, which delivers the quantum payload, responsible for the actual main part, which is seen in the top right. A forward-looking imager, which we use in cloud detection, which is on the left, and then a computer payload, which is responsible for the whole control of the payload and also the security aspects. The platform will be provided by another company. There's a small diagram at the bottom just kind of showcasing the basics of the concept. So the fly would be used to detect whether or not there'd be clouds. If not, we could then progress because the QKD link requires an optical link, which is inhibited by clouds. So when there's no clouds, we can then progress with that. And then classical RF just after. So I'll explain a wee bit about what a quantum key distribution is. Basically, it's a way to produce keys used in encrypting data. It's different from normal cryptography methods, as normal cryptography methods use complex algorithms to produce keys, which is fine for now, but with the advent of quantum computers, as I'm sure people have heard about, these insane computing power will be able to reverse these algorithms, break the keys, and then, making everyone's data very vulnerable. The reason the quantum key distribution is different is it relies on quantum mechanics to generate these keys, and that makes them like truly random. So they can't actually be like reversed in any way. We are going to be using the BB84 protocol. If you wanted to look into it, you can, but I'm not going to explain it today because it goes far too deep into it. But basically, there's a nice thing about that is during the actual creation of the key, by monitoring the error rate, known as the quantum bit error rate, we could actually determine if somebody has been eavesdropping on our link, which obviously is really useful when you're trying to keep security. At that point, if somebody had been listening, obviously we just abandon the link. So the right shows kind of like an example of the service architecture. The satellite would first deliver a key to one terminal. It would then deliver another unique key to another terminal, to then allow the two terminals to communicate with each other. The satellite would combine the two keys in an XOR function, deliver it to the ground. The terminal could then reverse it using its key, obtaining the other terminal's key, and then communicate securely through regular links. So the responsive operations side of this mission would be the cloud detection, as I've mentioned. Basically, the QKD link is really inhibited by cloud because as it uses optical photons, they can't progress through the cloud. So the main operation tasks are the cloud detection and then geolocating to actually determine where the clouds are in relation to the ground station, and then platform commanding, which allows the payload to overwrite the platform schedule and basically tell it where to point. So we can then, you can imagine then if you've got multiple ground stations, you don't want to point at the one that has cloud over it, you want to point at the one that doesn't have any cloud. So this allows for a really efficient use of resources, which on CubeSats are really limited. And also, as you're putting the operator kind of in space, you're reducing the operating costs, because with traditional satellites, an operator has to be on the ground telling the satellite exactly what to do and when to do it. So why have we gone for space-based QKD? Well, ground-based QKD does exist, and it's usually done through optical fibers. The issue with that is it can't go very far, so you end up having to have all these relay systems to make long-distance communication work, which again just leads that ends up creating all these security issues with loads of different attack points that a hacker could get into the system and take control of it. The good thing about space-based QKD is you're going for free space, so you've got less losses. You could then obviously have a satellite transmitting to one terminal at one side of the planet, in orbit, going around to the other side of the planet, transmitting again, and then those two terminals at the other side of the planet could communicate securely together. There is still an issue with losses in the atmosphere, and we get around this obviously by the cloud detection, as I've mentioned. We also would operate only at night, which removes any background light that may be picked up as noise, and we transmit from space to the ground, which is different from transmitting from the ground to space, because if you're transmitting from space to the ground, the atmosphere is only at the very last hurdle, whereas if you do ground to space, you have to go through the atmosphere and then onto space, which ends up leading to greater losses. So I'll give a short background on the methodology we've used for this project. So first, we decided model-based systems engineering over a document-based model because it formalizes the practice of system development throughout the whole life cycle. Yeah, it gives nice methods on behavioral analysis, system architectures, requirement traceability, performance analysis, simulations, and so on. Basically, it focuses on the visual and the actual architecture side, which is really easy to quickly see what's going on in a system. Whereas document-based, it's loads of text-based stuff, which no one likes. And yeah, the text-based stuff leads to issues in communicating of ideas, the speed at which you can update the project, and you run into issue of repetibility across different documents, which could lead to confusion if one document is outdated to the other. This method would allow just everything to be in one place really, which improves quality of the work and the productivity. To complement this, we use the System Modeling Language, or SysML, just the general purpose modeling language for engineering systems. Provides a common language to help communicate our technical information to other members, and it's based on common system concepts like requirements, behaviors, structures, and interconnections. It's derived from the Unified Modeling Language, or UML, but it removes a lot of the software-orientated information, focuses on the systems side of things. In addition, we also use the Zachman Framework for our project. This provides a structure on a way to view and define a project. The simplified version of this can be seen on the slide. You would basically start with the first row. You would answer all the questions, the why, the how, the what, the who, the where, and the when. And there's also a description of like what that means to the row. And as the project progresses, you would go down the rows until you have like a very detailed project at the end. It doesn't provide any methodology of how to actually get there, but it does identify the requirements at each stage of the project. So now I'll go into some of the examples of how we've used Enterprise Architect in our project. First of all, it would be the project requirements. So we've started at the very top level requirements, as you can see on the left-hand side. We would then work through that, developing the requirements further until we have like all the requirements needed. And then what we did was we linked them to various different parts of the architecture. The really messy diagram on the right kind of visualizes the fact that all these requirements are linked to different parts of the project. We also used Enterprise Architect to create our system architecture, basically trying to work out the design and all the components that we would need to actually create the payload. Again, we started at the very high level systems architecture, and when we allowed us to then go through and design the lower subsystem architecture that you can see in the right, which is a lot more complex than the high level. And the way we used Enterprise Architect is we could click through the block boxes as well. So if you click on this QPL, which is the quantum payload, it then brings up this diagram, which is really handy for quickly trying to learn what's going on in the project itself. We also utilized the check-in, check-out function with like version control to ensure that nobody could accidentally modify a diagram and ruin all this work. And also, if we ever want to go back to a previous design, we could easily do that too. In a similar way, we did state machine diagrams. These are basically diagrams, and each box shows an operational mode of the satellite, and the lines are basically the entry and the exit criteria for each mode. At the left shows a very, again, high level state machine diagram of just kind of overall system modes of the payload, and then the right shows an example of one of the actual subsystems, which has its own operation modes and everything in it. We then, so again, that was like you could click on the actual block on the high level and it would bring you to the subsystem, again, making it really easy to go through and learn about the design. The subsystem was then created given modes, and then those modes were then given its own sequence diagrams, which is shown here. Again, starting with a very high level sequence diagram. These basically just show the behavior of the mode and exactly the processes that occur during each mode. And then obviously we derive that into more detailed sequence diagrams, which these detailed diagrams could then be used by software engineers to go away and develop the actual software to run each mode. Another thing we did with the state machine diagrams is one person was working on combining it with simulation software. So he basically combined it with orbital mechanics, our cloud classification algorithm, and 42 simulation software to run a simulation of the mission in orbit of just the cloud detection. So you can see on the left, there's like the actual model with like loads of different reference frames, and then an example of the cloud classification at the bottom, and then the state machine that was running that is on the right. So what are the benefits that we found from using Enterprise Architect? Well, it allowed us to easily iterate designs. Like we'd start again at the high level, and we could easily work our way down without having to do too much changes. Obviously, then we had a localized area for all the project files, so everyone could work on it together. The check-in, check-out function really helped with that. Which obviously all that complemented the concurrent workflow of the design. So like one person could be working on one section, another could be working on another section, but without accidentally changing something on their section, which could corrupt the file. So the check-in, check-out function was extremely beneficial because obviously if you're working on it, you could check it out. When you check it back in, and then you put a comment in, so you could tell anyone what you've done, and the version control allowed for reverting back if an error occurred or somebody accidentally modified something that they shouldn't have. The project organization I felt was really good. I mentioned about how you could go through the blocks. Like if you started with the high level, you could click through and quickly find the lower level stuff. But also just the actual project browser itself was really good at maintaining organization, making it really easy to find different parts of the project. And for me, joining the company while ROKS had already been started on Enterprise, it allowed me to quickly learn about the project. We also used the document creation tools on Enterprise Architect to quickly export our work into our own format, which we could then send to other people who are involved in the project to when required, and that saved us loads of effort and time in creating documents. So my personal experience from using Enterprise Architect, as I say, I've only started Craft a bit less than a year ago. So I felt, and this is my first time ever using the software, I felt it was quite quick to pick up. And when I got stuck, there was loads of really helpful online documentation. I realized it's a really powerful tool to use in designing projects. Like it saves time, money, and resources, and it's a bit more, it's a bit nicer than just trying to write documents all the time. But as I say, from only having a little experience of it, I know that there's a lot more additional features that I could learn that could even enhance projects in the future even more. And I'm sure if any of you have any ideas, I'd be really happy to hear them. So I'd like to thank you for listening to my presentation. I hope it gave you a good idea of what the ROKS mission is all about. And if you have any questions, I'll attempt to answer them. Thanks.
Yeah, thank you. Thank you, Colin. Thanks for the wonderful presentation. So please stay connected with the Teams channel. If the people will start asking the questions over there, if there is any questions popping up on their mind. So please stay connected over there. So thanks once again, Colin. Thanks for the great presentation. Thanks for sharing your knowledge. Thank you all for the participation in this session. Please stay connected to Teams channel with Colin and other EA experts, and take forward with your conversations. If you find difficulties in connecting to the channel, please feel free to let us know. We will be staying in this session for some more time. If you have any difficulties in connecting the session, please drop us a note. We will definitely try to address it as quick as possible. Thanks all for the participation and your time towards this one. And thanks, Colin, once again.
Thanks.